Hello everyone, I'm Heng-Jui from National Taiwan University. Today, I'm presenting our work, Towards Lifelong Learning of End-to-End ASR. This is a joint work with Hong-Yi Li and Lin-shan. The major contributions of this paper are listed as follows. First, this is the earliest analysis for lifelong learning of end-to-end ASR. We adopted and comprehensively analyzed previous lifelong learning methods for this task. We also proposed two effective data selection methods to improve data-based approaches. This presentation is organized as follows. We first discuss why the lifelong learning problem of end-to-end ASR is crucial. Then, I'll describe how to achieve our goals, including regularization and data-based methods. Finally, a comprehensive set of experiments were conducted to evaluate the proposed methods. The main topic of this paper is to tackle the lifelong learning problem of end-to-end ASR. But why is this topic important, and what are the difficulties? First of all, the world is ever-changing, and so is our spoken language. This increases automatic speech recognition difficulty. For example, new acoustic environments, topic domains, speakers, or accents make ASR more challenging. So the long-term goal of lifelong learning is that ASR models can learn new data incrementally to synchronize with the changing world. For example, an ASR model is trained on domain A. Next, data from domains B and C are then used to fine-tune the model. After training, the final model can recognize data in domain C. But a very probable outcome is that the model cannot recognize data from the past domains. This is the phenomenon of catastrophic forgetting. So our long-term goal is to make the final ASR model be able to recognize data from all domains learned previously. Different from previous studies, we considered the lifelong learning problem of end-to-end ASR. End-to-end ASR jointly models acoustic and linguistic information in a single network, so this task is more challenging. We considered the connectionist temporal classification model here. In this part, I'll describe the main concepts of the methods we analyzed. A trivial solution is the fine-tuning baseline. This method trains ASR models only with new data and has no constraints. But this usually leads to catastrophic forgetting. On the other hand, the multitask learning upper bound retrains the model with all data. But this is very time-consuming and might have privacy or storage issues, so we cannot save all data. Therefore, we consider regularization and data-based lifelong learning approaches here. The methods here are previously designed for computer vision or reinforcement learning. Two categories of approaches are considered. For regularization-based methods, we use elastic weight consolidation, synaptic intelligence, and knowledge distillation. For data-based, we use gradient episodic memory and propose two data selection methods. Regularization-based methods use the best ASR model trained on a previous domain, denoted as theta A star. The model is frozen and used to regularize the new model theta B. The total loss function is composed of the original ASR loss and the regularization loss. EWC and SI constrain the parameters weighted L2 distance close to the previous model. This figure illustrates how they work, where the colored ellipses are the parameters with lower loss respectively on the two domains. The central points of the two ellipses are the optimal parameters. The blue arrow is the fine-tuning baseline, making the model moves from theta A star to theta B star, and leads to lower loss on domain B, but higher on domain A. Moreover, the red arrow indicates EWC and SI, making the model parameters move to lower loss on both domains. Also, knowledge distillation tries to constrain output distributions by minimizing the KL divergence. For data-based methods, they try to save some data from the past to constrain the current model. GEM is the data-based method used here, which constrains the gradient. First, we compute the gradients for data from the two domains. Next, if the angle between the two gradients is larger than 90 degrees, gradient B increases loss for the previous domain A. So we project gradient B to the nearest vector, making the angle less than 90 degrees. G tilde will then be used to update the model. These procedures are simply solving a quadratic programming problem. We also proposed two data selection methods. We found that the topic domain of each dataset varies. This might reflect different linguistic properties. For example, Wall Street Journal is composed of news, but the Liberty Speech dataset has much longer sentences from books. Also, Switchboard has short and spontaneous sentences from conversations. So we propose to choose samples with lower perplexities of transcriptions in their domains. Moreover, we found that the averaged sentence length in each dataset varies, reflecting different acoustic properties. The average durations of each dataset are respectively 10, 15, and 5 seconds. So we propose to choose samples with audio lengths close to the median of each dataset. In the last section, I will show the results of our experiments and the information they brought. In our experiments, the CTC ASR models were trained with Wall Street Journal, Liberty Speech, and Switchboard sequentially. In this order, the learning difficulty increases gradually. We first compare the multitask upper bound and the fine-tuning baseline. This figure shows the word error rates after training with all data. The final models are tested respectively on the three datasets. The blue bars show the results of the fine-tuning baseline. The significant increases of word error rates in the first two datasets clearly demonstrated the phenomenon of catastrophic forgetting. Now let's take a look at the averaged word error rate over the three datasets using different methods. With regularization applied, SI and KD surpassed the fine-tuning baseline, where KD performed the best so far. Probably because the differences between these methods, EWC and SI constrain each parameter from drifting too far. Instead, KD constrains the output distributions, which offers parameters more flexibility. Next, with 30 minutes of past data preserved, data-based methods provided even better performance. The results show that learning from the past data offered more freedom for the model parameters to learn sequentially. Also, the proposed data selection methods are better than the original random selection. Furthermore, we compared the learning curves of using different methods. We chose the fine-tuning baseline, the best regularization-based KD, and the best data-based GM with the proposed data selection. We now inspect the learning curves. The horizontal axis indicates normalized training steps, and the vertical axis shows the word error rates respectively on the three datasets. The red curves here are the fine-tuning baseline. The yellow ones are knowledge distillation, and the blue ones are GM with the proposed data selection. We focus on the upper right part of this figure to observe the performance changes on the first two datasets. First, the increased word error rates indicate severe catastrophic forgetting occurred when using fine-tuning and knowledge distillation. But GM had less forgetting. Next, the first two methods made the learning curves oscillate severely. In contrast, the curve of GM is more stable. So we conclude that GM mitigates catastrophic forgetting and stabilizes training. Furthermore, we investigated the impact of saved data. The horizontal axis is the amount of saved data for GM, and the vertical axis is the word error rate. The red, orange, and blue points here are respectively error rates evaluated on Wall Street Journal, Liberty Speech, and Switchboard. These points used 30 minutes of data which have the same setting as the experiments discussed earlier. We note that saving 0 minutes of data is the fine-tuning baseline. Also, saving 220 minutes of data uses the same capacity as the regularization methods for keeping the previous ASR model. The solid curves here use the proposed Lin method, and the dotted curves are the results without the proposed data selection. First, with more saved data, the ASR model performed better on automates. So it's clear that a small amount of data helped. Also, the proposed data selection is better than random selection. In conclusion, we adopted and analyzed various lifelong learning methods for end-to-end ASR. We found data-based are better than regularization-based approaches for ASR. And the choice of saved data is important. Finally, the task of lifelong learning of end-to-end ASR is a long-term goal. This is the end of our presentation. More details can be found in a paper. Thanks for listening.